Hello, this is question 3 from the 2008 MAT. So we got the graph y equals f of x of a certain function has been plotted below. Next three pairs of axes a, b, c are graphs of y equals f of minus x, f of x minus 1 and minus f of x. Say which one is which. Right, so if we've got y is f of minus x, that's our reflection in the y-axis, which is what, the middle one. So that is f of minus x. Then we've got f of x minus 1, so that's shifting 1 to the right, which is this one. And then we've got minus f of x, which is our reflection in the x-axis. So that is the first one. Right, okay, that was a nice easy starter. Part 2, sketch on the axes opposite graphs of both of the following functions. Well, I'm going to write these out a bit larger because I can barely read them myself. Y equals 2 to the minus x squared and y equals 2 to the 2x minus x squared. All right, okay, that second one looks particularly horrible. How are we going to go about, oh, it says carefully label any stationary points. Right, let's just worry about the first one then initially. Let's get a point on the board. When x is 0, we've got y is 2 to the power 0. So it's going through 0, 1. So let's go there, put that on and say that is 1. Now we've got the, what else can we say about this? So this is saying that y equals 1 over 2 to the x squared. So this is going to be symmetrical about the y-axis because whether we've got positive x or negative x, it's going to square up and give the same value. So it's symmetrical about that point. What happens as x gets bigger and bigger, y is getting smaller and smaller, but it stays positive. So we are tending off to infinity on either side. So we can say here, so as x tends to plus or minus infinity, y tends to positive 0. So that's certainly something that we've got. And we can say that, so what's happening here is x increases from 0. So as x increases from 0, what's happening? We're getting these, they're always going to be positive powers of 2, but we're going through roots of 2 up until x is 1. So x is 1, x equals 1, we're going to have that y equals a half. So it's got to go through that point, and then the same over there. And then, so we're going through various roots, which is meaning we're still going to be less than 1 because we're going 1 divided by various roots of 2. And then it's just getting bigger and bigger. Yeah, we've just got a smooth, we just got this sort of smooth curve going up, something like this. Try and get it. Oh, I've missed that x, but you get the idea. Try and make it symmetrical and label the turning point. So we've got a turning point there at 0, 1 is the maximum. Right, so how on earth are we going to make this second one? How are we going to get a sketch of that? Because that looks unpleasant. They've put us in the mindset of transformation. So we want to try and, we can see it's not a million miles away from what we've already drawn. So how are we going to get this into that format? Now we've got this quadratic here. When it comes to rearranging these to get them into a transformation of graph, because you might be thinking, well, let's factorize that into x2 minus x, because that is our 2x minus x squared. But that's not putting it in a format which is one of our transformations of graphs. Yeah, we want to have things where we're, well, particularly doing something like this f of x minus 1, something along those lines is definitely something that we want to be looking for as a format. So factorizing that way doesn't help us that much. Whereas if we complete the square, then it does help us because we'll be getting it into that format. So we've got here minus x squared minus 2x. That is what we've got. I just like taking the minus sign outside so I don't do something stupid when I complete the square. Then we can complete the square on that and say that is minus, so that would be x minus 1 squared. So we'd have, yeah, our x squared minus 2x, then plus 1 becomes a minus 1, so we have to add plus 1 on the end. So this is going to be the same as y equals 2 to the minus x minus 1 squared plus 1. So we can see this minus x minus 1 squared bit, that is a transformation of our original graph. We just need to deal with this plus 1, which of course is the same as multiplying by 2 on the, if we're not in a power, as in that will be 2 times 2 to the minus x minus 1 squared. So that is our rearranged function to give us two transformations, a stretch by 2 in the y direction and a transformation of 1 in the positive x direction. So that's our two transformations we got there. So move it across 1 and then stretch by 2. So our peak has gone up here. So that's going to be the maximum. Again, it's got to be symmetrical around this. And what happens when x is 0? When x is 0, going back to the original format, we're still going through the same point. So it's also going through that point there, which means it's going through that point there. Is it going to be below the blue line? I think it's pretty much going to have to be below the blue line. But how do we actually check on this? So say we had x was, well, I don't know, 1. Then if x is 1, then we know that's, no, 1's not a good example. It's too close to where we are. So say x was 10, say. So if x is 10, then we've got, for the first one, y is going to be equal to 2 to the minus 100. And for the second graph, y is going to be equal to 2 to the, what is it going to be? If x is 10, then we've got 20 minus the 100, so that would be minus 80. That's if x is 10. If x was minus 10, you'd get minus 100 and minus 120. So yes, this is all fitting. The reason I'm doing this, I just want to make sure that the red line is below the blue line on this side, which it is, and then going through here and up to the peak, and then it's above the blue line on the other side, which it is. That's what these things are showing. The fact that this is an 80 and that's 100, that means that red line's above the blue on this side, and that you'd have 100 and 120 means the red's below the blue line on that side. So that's our graphs there. So this is at 1, 2 for our turning point. Right, that was pretty involved drawing those out. What we got for part C then? Let C be a real number and define the following integral. Okay, so this is, let's just write that integral out a little bit larger. We've got 0 to 1, 2 to the minus x minus c squared dx. Okay, so that's looking like this second function. State the value or values of c for which I of c is largest. Briefly explain your reasoning. Note you're not being asked to calculate. So they're asking us about this graph that we just drawn. So actually this is useful then, that if you've not been able to draw something out in the previous part of the question, then this gives you a bit of a hint that you can get this second function into that format. That would certainly be the case. So we're integrating between 0 and 1. So we're integrating in that region for this red function. And we want to maximize the area. So we're going to want to get the peak in the middle of the region. So this is equivalent to, so how are we going to briefly explain? So this is equivalent to the red graph, red line, or however you want to label it, you might say, or second function, anything which is drawing their attention to the second thing you drew on the graph. And the C is translating left and right, left to right, or right to left, whichever way you want to move it. So maximum area when peak is in middle of the integration window. So peak at x equals a half. So that's certainly what we want there. So that means that is the value of c. That is what we want. Therefore, we need that c equals a half. That's just dropped straight out. We can see that here that 1 is where we've moved the peak to the x coordinate of 1. because we've started with this base function here where the peak is at 0. So whatever C is moving this peak of the first graph, the blue line, it's moving it left and right. And we want to get that peak to the middle of the integration window. So we need C to be equal to 1/2. Right, okay. So, I mean, actually, you could say, I mean, I've said this is equivalent to the red line. It's actually equivalent to the blue line as well. So that might have been an even better way of putting it, because this is the same. This is closer in the original format to the blue line. I was just getting fixated on the red one because I just rearranged it into that format. But actually, you could say, yeah, this is equivalent to the blue line, and C is moving it side to side. So it doesn't matter which line you pick. You're just saying that C is the thing that's translating it in the X direction. Right, that was, yeah, an interesting question, that one. It started easily, it ended fairly easily, but the graph sketch was not that trivial in the middle, although, you know, sort of worked through it okay in the end.